All right, let's get started with lesson 4, the pH scale. Now, the pH scale is a quick and easy way for us to determine how basic or how acidic a particular solution is. The pH can be found by taking the negative log of the hydronium ion concentration. So in other words, the pH is dependent upon a log base 10 scale of the hydrogen ion concentration. So you could look at it also, the pH is equal to the negative log of the hydrogen ion concentration, which of course is the same as the hydronium ion concentration. pH numbers are usually positive and there are no units to pH. The pH number is inversely related to the H plus concentration. So in other words, you can view it as this, as the H plus concentration goes up, the pH goes down. So the more acidic solutions have low pHs and high concentrations of H pluses, and the more basic solutions are going to be reverse of that. They're going to have low hydrogen ion concentrations and higher pHs. So since the pH scale is based on a log base 10, we get these positive numbers in a scale ranging from 1 to 14. Now, since we just quoted that the H plus concentration is inversely proportional to the pH, what we find is that pHs that are essentially below 7, the H plus concentration, or the hydronium ion concentration, is going to be greater than the OH minus concentration. At pHs greater than 7, the hydronium ion concentration is going to be smaller than the hydroxide ion concentration. So it becomes more alkaline or basic above pH of 7 and more acidic below pH of 7. So what happens at a pH of 7? Well, you probably already know this. The hydronium ion concentration is equal to the hydroxide ion concentration, and we have what is called a neutral pH at a pH of 7. All right, so the lower the number, then the more the greater the hydronium ion concentration is, and the stronger the more acidic the acid strength of the solution is. And the higher the number, going up to 14, the more basic the solution is, and the greater the hydroxide ion concentration, and the lower the hydronium ion concentration would be. All right. Now, I want to make note of this because this is really important, that this particular pH scale, with 7 being neutral, is based on the temperature of our situation being 25 degrees C. All right. Now, if we change the temperature from 25 degrees C, then we will change the neutrality point. We'll still have a pH scale of 1 to 14, but the neutral point can change. So we always essentially based our pH scale that you're familiar with at 25 degrees C. All right. So don't forget that. Now, the other thing about these numbers is what do they mean exactly, being based on a log base 10 scale? Well, as we move from one number to another number, it changes by a 10-fold. All right. So for instance, if we go from a pH of 4 down to a pH of 3, that's going to be a 10-fold increase in the hydrogen ion concentration. So the hydrogen ion concentration is now 10 times stronger, going from a pH 4 to a pH of 3. The same thing you could say if you went from a pH of 3 to a pH of 2, it's a 10 times increase in the hydrogen ion concentration. That's really important to understand what these numbers mean. So there is a big difference going from a pH of 3 to a pH of 2. Going up is the same idea. If you're going from a pH of 9 to a pH of 10, it's a tenfold increase in the hydroxide concentration, or in other words, a tenfold decrease in the hydrogen ion concentration. All right? And that's all because of the log base 10 scale. So again, a change in 1 pH unit represents a tenfold increase in the H plus concentration. So let's go ahead and use our pH equation now to solve some pH problems that we will encounter for the AP and IB exam. So the first one we have here, example 1, it says calculate the pH of a solution containing a hydroxide concentration of 0.02 molar. All right. So since the pH scale is based on the H plus concentration and not the OH minus concentration, we need to actually calculate the H plus concentration using the hydroxide ion concentration. To do that, if you recall, we know that Kw is equal to the hydroxide concentration times the hydronium ion concentration, or the H plus concentration. Therefore, the hydronium ion concentration is equal to Kw over the hydroxide ion concentration. All right? So, with that relationship now between Kw and OH concentration and the hydronium ion concentration, we can now plug in Kw value and divide that by the hydroxide concentration that we have in our solution, 0.02 molar. And that will give us a value of 5 times 10 to the minus 13 molar. That's going to be our H plus concentration. So H plus then, or the hydronium concentration, ion concentration, is 5 times 10 to the minus 13 molar for this particular solution. So now we have what we need in order to solve for pH. So now we just take the pH scale is equal to the negative log of the hydronium ion concentration. So we plug that in for pH, negative log of 5 times 10 to the minus 13. Take the negative log of it, and we should find that the pH is equal to 12.3. Right? So in other words, our pH for this particular solution is 12.3. Right? It is a high number, so it's very basic, which should make sense because if you look at it, our hydronium ion concentration of 5 times 10 to the negative 3, hydronium ion concentration, is smaller than the hydroxide concentration of 0.02 molar, right? So therefore, it should be above 7, which it is, and it tells us that being 12.3, it's a fairly basic solution, all right? So there's one problem. Let's do another problem here. All right, so now we have a solution has a pH. So now we know what the pH is. The solution has a pH of 4.5, and now we need to calculate the hydroxide ion for the particular solution. All right, so this is going to be a little bit backwards of what we did in example problem 1. So first of all, we know that we can find the hydronium ion concentration from the pH. And we can do this because we know that the pH is equal to the negative log of the hydronium ion concentration. So to find the H plus, or the hydronium ion concentration, what we have to do is take the inverse of the negative log. So on your calculator, where you have your log button, the LOG button, above it usually there's, so if you have a log button, LOG, above it is a time 10 to the X button. That's what you need to do to push that button in order to get the inverse log base 10. So you push that, and then you're going to put in negative, because remember it is the negative log, so negative pH, which is 4.5, and that will give us an answer of 3.16 times 10 to the minus 5. All right, so that should equal the hydronium ion concentration at a pH of 4.5. All right. So, and also remember that a pH of 4.5 is on the acidic side. It's not highly acidic, but it is acidic enough that we should find that the hydronium ion concentration in the end should be bigger than our hydroxide ion concentration. Okay, so now we can go ahead and find the hydroxide ion concentration by again using the Kw is equal to the hydroxide ion times the hydronium ion concentration. So therefore, hydroxide ion concentration can be found by taking Kw over the hydronium ion concentration now, which is equal to 1.0 times 10 to the minus 14. That's the Kw value for water. And then the hydroxide concentration, which we just found, was 3.16 times 10 to the minus 5. We do the math, and we get a 3.16 times 10 to the minus 10, which is the concentration of the hydroxide. All right? So that's pretty much how we solve problem number 2. And again, we were right. The hydroxide concentration is smaller than the hydronium ion concentration, or the H+. So you could say that the H+ concentration is greater than the hydroxide concentration, which we would assume because the pH is as low as it is. All right? All right, so there we go. So just remember that if you want to if you're given the pH and you need to find the hydronium ion concentration, you have to take the inverse of the log base 10. All right, so you're 10 to the x button. And also make sure you don't forget you need to take that negative. That's important. All right, let's go to POH now. All right, now POH is a very nifty and handy little scale. The POH scale is not often used much unless you're doing chemistry. But it can be very fast and very quick to help us with pH a lot, okay? So what is the POH scale? Well, the POH scale is based on taking the negative log of the hydroxide concentration instead of the hydronium ion concentration, all right? Now the scale is, because it is base 10, log base 10 scale, the high point is 14, the low point is 1, with 7 in the middle, except the fact the scale is inversed. In other words, the hydroxide ion concentration is greater than the hydronium concentration, or the H+ concentration, at pH's, or POH's, remember POH's scale, under 7. And anything above 7, the hydroxide concentration is going to be less than the H+. So it's just flipped around. And 7 is still neutral. The H+ and the hydronium, or the H+ and the hydroxide concentration are equal, as long, again, as this is based on a 25 degrees Celsius temperature. All right, so that's kind of something to note. Now, why is this so nifty? Well, it turns out that there's a relationship between POH and pH. If you take the POH and you add it to the pH, you get a value of 14 every time because of the log base 10 scale. So you can use this equation right here. In fact, this is an equation you should memorize. You should memorize because it makes your pH calculations and pOH calculations super fast. All right, because all you need to do to find the pH, for instance, is take 14 minus the pOH, and you get the pH. Or you can take 14 minus the pH, and you can get the pOH. All right, and there will be some calculations that you'll want to use this relationship because it will make things faster and easier for you using the pOH scale. All right, so for example, let's look at a problem where we would use this relationship. So example problem 3, a sample of a freshly pressed apple juice has a pOH of 10.24. So again, a pOH now, not a pH of 10.24. And we need to calculate the H plus concentration. Well, using our nifty little equation of pOH plus pH is equal to 14, we can take 14 minus the pOH, and that will give us the pH. So 14 minus 10.24 is equal to the pH of 3.76. Okay, so that's our pH. It's a low pH, so our solution is acidic. All right, so now we're not done with the problem though, because now we need to still calculate the H plus concentration. So what we do know then is that the pH again is equal to the negative log of the H plus concentration, right? So therefore, if we take the inverse log, so to find the H plus concentration, we can take the inverse of the log base 10 to the x button again, the negative pH. What we can do then is solve for our pH by taking negative 3.76 inverse log, which gives us a value for the H plus 1.74 times 10 to the minus 4. All right, and that gives us our H plus concentration, or which is also equal to the hydronium ion concentration, right? Remember, they're the same. The H plus is just a simplified version of the hydronium ion. All right, so there's an example of how we use pOH and pH together to solve for the hydronium ion or the H plus concentration. Now we could, this could be reversed. In other words, we could, in our previous problems, if we go back, let's go back to problem number 2, we could use that relationship that we just looked at now, pOH plus pH, to actually solve for the hydroxide concentration really quickly, because you could go to basically 14 minus the pH, which is 4.5, and that would give us the hydroxide concentration, right? Or the, not the hydroxide concentration, sorry, the pOH. And then once we know the pOH, you can take the pOH is equal to the negative log of the hydroxide concentration. Take the inverse of that, so in other words, the hydroxide concentration can be found by taking the negative pOH value and the inverse of that. And then that would give you the OH concentration. So that's another way of doing example problem 2 of looking at the pOH and the pH relationship, okay? So hopefully this all makes sense to you. So this is it for this particular lesson on pH and pOH scales. So that's it for now. Now, I do want to mention, though, pH and pOH are really important topics and for you to understand, okay? So study it well. And that's it for now.